In this final video, we're going to go through some practice problems for game theory. Our first question, we're going to start with just identifying the dominant strategy in normal form games. So just so you get some practice analyzing these games. All right, so our first one here is between Alice and Eve. Alice and Eve are two rival chefs competing in a cooking competition. Each chef has to decide whether to prepare a dish using a secret ingredient or a popular ingredient. All right, so we want to know which strategy each one of them is going to choose and where our equilibrium is going to be. So we're going to start with Alice and analyze her payoffs. So let's start with assuming that Eve is going to place a secret ingredient. In that case, Alice gets 3 units of payoff if she also plays a secret ingredient, and she gets 4 if she plays a popular ingredient, right? So that's her choice in the instance when Eve plays secret ingredient. If Eve instead plays a popular ingredient, excuse me, then Alice also prefers to play a popular ingredient. So we can see that popular ingredient for Alice is a dominant strategy. She's always going to pick that action regardless of what Eve does. All right, so we can go ahead and circle that. Now for Eve, we want to evaluate what she will do given that Alice is always going to play a popular ingredient. If she plays a secret ingredient, she gets a payoff of 1. If she plays a popular ingredient, she gets a payoff of 2. 2 is better than 1, so she's also going to do popular. So we end up in this cell popular ingredient, and that is the Nash equilibrium. And so each player's dominant strategy in this case is going to be to play the popular ingredient. Okay, whenever Alice plays secret ingredient, Eve wants to play popular, and the same is true for Alice. Okay, so it looks like is a type of prisoner's dilemma game where the Nash equilibrium is below the Pareto optimal equilibrium. Next, let's look at Bob and Frank. Bob and Frank are two tech entrepreneurs who are launching different new products. They must decide whether to innovate with cutting edge technology or just improve their existing technology. Okay, presumably they're in competition with each other. So again, we're going to start by analyzing Bob's options and assuming that Frank plays innovate. Bob is going to select improve. Right? If Frank instead plays improve, then Bob again, we see will play improve. So here, Bob's dominant strategy is improve, excuse me, just to play improve. So that's what he's going to play every single time. So Frank knowing that, right, knowing that Bob is always going to play improve, now we want to know what Frank's going to do. So if Frank innovates when Bob improves, Frank gets a payoff of 2. If Bob improves when, if Frank improves when Bob improves, then he gets a payoff of 3. And so we're in that improve cell. That is the Nash equilibrium. And both Frank and Bob have a dominant strategy of improve. Right? Regardless of what Bob does, Frank is going to play improve. So, and then the same for Bob. Whatever Frank does, Bob will play improve. Our third game here is between Charlie and Grace. Both are artists competing at an exhibition. They must decide whether to create a traditional piece of art or an abstract piece. So let's start with Charlie and see what his payoffs are when Grace plays traditional. Here, when Grace plays traditional, Charlie prefers abstract. And then when Grace plays abstract again, Charlie prefers abstract. So abstract is Charlie's dominant strategy. Grace, knowing that Charlie's always going to play abstract, is facing the choice between a payoff of 1 when she does traditional and a payoff of 2 when she does abstract. And so her dominant strategy is abstract as well. And the Nash equilibrium is at 2-2 cell. Our final game here is between Hank and David, who are both two politicians running for office. They must decide whether to focus their campaign on one of 3 sets of policies: economic, social, or environmental. All right, so let's analyze this. We're going to focus on David and then turn to Hank. So let's assume that Hank chooses economic policies. What is David going to do? Looking at his trade-offs, we see that he's going to select environmental policies because that gives him the highest payoff. If instead Hank selects social policies, Looking at all of David's payoffs, we see again environmental gives him the greatest payoff. And then finally, when Hank does environmental policies, we see again for David, environmental policies give him the largest trade-off. So he is again, not again, excuse me, but his dominant strategy, David's dominant strategy, is going to be environmental policies. Now, Hank, knowing that about David, knowing that David's always going to choose environmental policies, wants to compare his payoffs between economic, social, and environmental. And we see that for Hank, when David plays environmental, his highest payoff is from environmental policies as well. And so the Nash equilibrium is when both emphasize their environmental policies for their campaign. Okay. So those are four different games we've analyzed. They all happen to have Nash equilibriums in that bottom right cell, or just out of happenstance. But you can hopefully see the process by which we would go about analyzing a game. All right. Now let's move to question two. So question two, three, and four are all going to use this same normal form game. All right. We're going to be referring to it three times. In this first one, right, this gives us the setup. So we are part of a cartel that exports rare minerals, one of two countries. And demand conditions are such that various combinations of these rare minerals yield profits as listed in the payoff below. If we cooperate and collude with this other country, then and only produce 500 tons, we both earn $300 million of profit. If instead one of us cheats, like let's say I cheat and produce 1,000 tons while the other country produces 500, I get 400 million in profit, and my partner in this cartel only gets 150 million. If I cooperate and my partner cheats, they get 400 million and I get 150. And then if we both cheat, we each get 200 million. Okay, so that's how that game plays out. All right, so part A of question two. If both of us countries successfully collude, how much will we each produce? All right. And then what will our profits be? So successfully colluding means each of us are sticking to our agreement to restrict output. So that means that we're going to be operating in this produce 500 tons cell. And so our equilibrium outcome is going to be that produce 500 tons, produce 500 tons. And we each earn a profit of $300. All right. So for A here, that equilibrium is produce 500 tons and then produce 500 tons. And profit for each will equal 300 million. Okay. Part B asks, what is the equilibrium outcome if the game is only played once? Is this outcome beneficial for your country? Okay, so B, if the game is only played once, looking at this game, we can see it's a prisoner's dilemma. I have an incentive to cheat because it gets me a payoff of 400 rather than 300, and so does my partner in this cartel. So if we're only playing once, both of us are going to probably give in to this incentive to cheat because we're not anticipating playing any more after this. All right, so we're going to try to get as much as we can. We have this incentive to cheat. We both cheat. And as a result, we end up in this produce 1,000 equilibrium. Where we each earn less, right? And that is 200 million rather than the 300 when we cooperate. So we are, in fact, not better off. It is not beneficial. We would much rather be in that cooperate equilibrium instead. All right, moving to question three. So question three says, okay, we're facing the same game. Now, however, we're playing indefinitely, so it's an infinitely repeated game. And the question is, if we adopt a Grimm strategy, that we will cooperate as long as the other country does, and they're doing the same. We want to know first what our stream of profits is if we both cooperate. And then B, if I cheat in the first year? And then C, is a discount rate of 0.6 enough to incentivize cooperation? And then what about 0.95 and 2 for D, zero point 0.2 for D? And then finally, they want to know at what level of discount is my country indifferent between cheating or abiding by the agreement. All right. So let's start with A. So what is our stream of profits if we cooperate? So here we're going to have an infinite sum, right? An infinite series. Because again, we don't know how many rounds are in this game. It's infinitely repeated. No clue when it's going to end. All right. So our profit here is going to be that $300 we get from cooperating in the first round, and then that same payoff, but discounted for every period in the future. All right, so initially in that first round, we have d to the 1 power times 300 plus d squared for that second period in the future times 300, and so on until we get to d to the infinity times 300. Okay, so that is our sum of our profit if we both cooperate in this case. But instead, let's say that in that first round, we cheat, my country cheats. So what that is going to mean for our profits is I get the payoff from cheating when the other country doesn't. And then from then on, my cartel member is never going to cooperate with me again. And so that infinite series is going to be the discount rate um, squared, cubed, and so on times 200 to the infinite round. Okay, so that is B. D wants to know, is a discount rate of 0.6 enough to incentivize cooperation, or will we cheat? So let's see. So now what we can do is compare these two values, right? We want to know what that difference is. So see, we're going to have is 300 plus 0.6. Actually, you know what? Let's go ahead. Before we do that, should be 200. We're going to rewrite these as infinite series. So remember that for an infinite series, we can replace it by d over 1 minus d, right, times whatever that value is. All right, modifying the discount rate. So our profit from cooperating is going to be 300 plus the discount rate over 1 minus the discount rate times 300. And we want to know how that compares to our profit from cheating, which is 400 plus d over 1 minus d times 200, which is the profit again from cheating. Okay, so let's see. So we have 300 plus 0.6 over 1 minus 0.6 times 300, and we want to know how that compares to 400 plus 0.6 all over 1 minus 0.6 times 200. Okay, so from here, we're going to have 300, we're just simplifying, plus 0.6 over 0.4 times 300. How does that compare to 400 plus 0.6 over 0.4 times 200? And then 0.6 divided by 0.4 is going to give us 1.5. So we'll have 300 plus 1.5 times 300. We want to know how that compares to 400 plus 1.5 times 200. 1.5 times 300 is going to give us 450. So 300 plus 450. And how does that compare to 400 plus 300? Okay, so what we see here is that the payoffs from cooperating, in this case, exceed the payoffs from defecting. And so at a discount rate of 0.6. Um, both firms will, or both countries, I guess in this case, both countries will cooperate. Now, keep in mind from the lectures that the discount rate essentially says how much the firm values future dollars now, right? So the discount rate says that we value a dollar tomorrow at 60 cents today, okay? So at 0.6, we'll cooperate. At a discount rate of 0.95, that's above 0.6. So we definitely cooperate, right? That means we really value future dollars very highly. And so cooperation is really not a question, especially since we cooperate when the discount rate is 0.6. We want to know at 0.2, will the countries cooperate? And what we can do here is take this general form of our cheating payoff and our cooperation payoff and solve for the value of the discount rate that will incite cooperation. All right, and we can compare that to 0.2 to see if that is enough to sustain cooperation. So what we're going to do here is subtract 300 from both sides and subtract d over 1 minus d times 200 from both sides. Okay, and in this case, it's not a question of if the cooperative profit is greater than the cheating. We want to know the discount rate for which the profit from cooperating, it does exceed the profit from cheating. All right, because I believe it says, oh no, oh, that's the next one. Wants to know when we're indifferent. Okay. All right, so here, we're going to go ahead and do all this arithmetic. So we'll have d over 1 minus d times 300. This should be 200. Minus d over 1 minus d times 200. And then on the right-hand side, we have 100 left, right? 400 minus 100 is going to give us, 400 minus 300 is going to give us 100. Okay, so on our left-hand side here, we have d over 1 minus d modifying 300 and 200, so we can pull that out. So we'll have d over 1 minus d multiplied by parentheses 300 minus 200. Okay, that's going to give a, all greater than 100. That's going to give us d over 1 minus d times 100, all greater than 100. From here, we want to eliminate this fraction. So we're going to multiply both sides by 1 minus d. Okay, that's going to give us 100 times the discount rate being greater than 100 times 1 minus the discount rate. And we're going to go ahead and distribute that 100. So we'll have 100 times d greater than 100 minus 100 times d. We're going to add this 100 times d to both sides. And that's going to give us 200 times the discount rate greater than 100. And then finally, we'll divide both sides by 200. And 100 over 200 gives us 1/2. And so we find that as long as the discount rate is above 1/2, the firms, or in this case, the countries, will cooperate. So that discount rate of 0.2, that is going to be less than 1/2. And so at a discount rate of 0.2, the firms cheat. Okay. And then our last thing here, what discount rate will make these firms indifferent? And it's going to be the discount rate equal to 1/2, right? At the discount rate equal to 1/2, we should see that the payoffs from cooperating equal the payoffs from defecting. Let's go ahead and check to make sure we're correct there. So we're going to go ahead and copy this general form again. Move it down. All right. And now we want these to be equal, so we're indifferent. So if we substitute 1/2 for our d, we'll have 300 plus 0.5 over 1 minus 0.5 times 300 equal to 400 plus 0.5 over 1 minus 0.5 times 200. Then we'll have 300 plus zero point 0.5 over 0.5 is going to give us 1. That'll be 300 equal to 400 plus zero point 0.5 over 0.5, that's 1, plus 200. And we were correct, right? The payoffs when the discount rate is 1/2 are equal whether the firm cooperates or defects. Okay, so that was question 3. Let's go ahead and write that so we know. This is oops, question 3. Let's move on to question 4. So question 4, again, we're playing the same game, but now rather than using a Grim trigger strategy, both of us are using tit for tat. Okay, so what is going to be our stream of profits if we always cooperate and our opponent uses tit for tat? Essentially, it's going to be the payoffs when we just cooperate and there's no strategy in question, right? We just do. So let's go ahead and write that out. So here we're looking at question 4. Let's go ahead and make it obvious. Can you see that? No, not really. Okay, question 4. All right. The payoffs from cooperating, they're going to be 300 plus discount times 300 plus the discount squared times 300 and on to infinity, right? Because we're cooperating forever. Okay. All right, so that's A. B, what is the stream of profits if we defect once and our opponent plays tit for tat? Okay, so let's say that we defect in that first round just to make it easy. So defect once. We're going to get the payoffs from defecting when our opponent's cooperating, and then in the next round, we're going to cooperate, but because we cheated in the previous round, our opponent's going to cheat, which makes our payoff in the second round 150. And then from there, since we cooperated, our opponent will also cooperate, and so we're both now just cooperating indefinitely. Okay, so that's what those payoffs are going to look like. And just so you can see here, right? So in that first round, we were in this cell, right? And then because we cheated, in the next turn when we cooperate, our opponent cheats. Okay, so that's how we get those first initial payoffs. And then from there on, we're cooperating, so they're cooperating, so we get 300 sustained. Okay. Turning to C, at a discount rate of 0.7, is it worthwhile to defect? Okay, so again, we want to compare the profits from cheating once to the profits from cooperating. Okay, and then if it is worthwhile to defect once, would it be worthwhile to defect more than once? All right, given the discount rate of 0.7. So looking at C, we want to know, how does the profit from cooperating compare to the profit from defecting once when the discount rate is 0.7? All right. So from here, what we're going to go ahead and do is take our two sums that we just wrote out, and we're going to copy them like we did before and set them up to explore their relationship. Okay, so we'll have this, and we want to know, how does that compare to the payoffs from defecting once? Okay. All right. All right. So from here, the first thing I'm going to do right away is notice that from d squared on, this infinite series is exactly the same. Okay, so I'm just going to subtract those values from both sides so we don't have to deal with that portion of the series, okay, because they're just going to cancel out. They're exactly the same. What really matters is these first two rounds of payoffs when we defect and then resume cooperating with an opponent playing tit for tat. So doing that subtraction, we're going to end up with 300 plus our discount rate times 300. And we want to know how that compares to 400 plus our discount rate times 150. We're going to subtract 400 from, well, let's subtract 300 from both sides and subtract the discount rate times 150 from both sides. And that's going to get us discount rate times 300 minus the discount rate times 150 on the left. And we want to know how that compares to 100. We can pull out this discount rate since it's modifying both 300 and 150 and be left with the discount rate times 300 minus 150. And we want to know how that compares to 100. And then simplifying, we have the discount rate times 150, and how does that compare to 100? And finally, our discount rate, of course, is 0.7 times 150. How does that compare to a payoff of 100? So we'll get 0.7 times 150. That's going to give us 105. And that is, of course, greater than 100. Okay. And so it seems that for our purposes here, cooperating is going to have a greater payoff than defecting. Okay. All right. Cool. Another way we could do this is just substitute for that discount rate at this stage, at this second, once we've eliminated the parts of the infinite series that are the same. So we would have instead 300 plus 0.7, our given discount rate, times 300. And we'd want to know how that value compares to 400 plus 0.7 times 150. Okay. So on our right-hand side here, we'll get 400 plus 105. And then on our left-hand side here, we're going to get 300 plus 210. And so we have 510 for the payoffs from cooperating and 505 for the payoffs from defecting. And so we can see again, cooperating pays off. So at 0.7, it's not worth defecting. Okay. Even once. All right. And then since it's not worth defecting once, it's not going to be worth defecting multiple times. So not worth. Okay. And then part D asks us for what values of our discount rate does defecting make sense at, or in other words, is it worth it? All right. So D here, we want to know what will make the payoffs, what discount rate makes the payoffs from defecting exceed, let me try that again, exceed the payoffs from cooperating. Okay, that's what that question is asking. So let's go ahead and copy over our payoffs in their general form. Looks like we lost a couple lines here. So it's 300 plus the discount rate times 300. That's our payoff from cooperating. And we want to know what discount rate will make that less than the payoffs from defecting, which is 400 plus the discount rate times 150. Okay. So here we're just going to solve for the discount rate. So I'm going to subtract 300 from both sides. And I'm going to subtract the discount rate times 150 from both sides. Oops. That's going to give us the discount rate times 300 minus the discount rate times 150 less than 100. Again, the discount rate's modifying both 300 and 150, so I can pull it out. So we have the discount rate times 300 minus 150, and that's less than 100. So that discount rate now is 150. excuse me, that discount rate times 150 needs to be less than 100. So we're going to divide both sides by 150, and we're going to be left with a discount rate of 100 over 150, which is equal to 2/3. So that discount rate needs to be less than 0.66 repeating. Okay, all right. For defecting to be worth it. Okay. All righty, righty. And then the next part of that question, how does the value of defecting change as the discount rate changes? Essentially, as the discount rate falls, the value of $1 in the future becomes less. And so the value of defecting is going to, I would think, grow as that discount rate falls. So if we had 150 times 0.2, that's 30. 150 times 0.66, that's 90. Um, yeah, so the value of defecting grows because the value of cooperating is going to fall, right? They're both going to fall, but what we'll likely see is the value of cooperating falls faster than the value of defecting. Okay, and thus it's more attractive. All right, moving to question 5. So here's just practice with decision trees, just using backward induction to identify the equilibrium of this game. And this one's a little more complicated because we have 2 players with Andre and Basie. And in this game, Andre's the first mover, and then Basie moves, and then Andre moves again. Okay. And so again, what we're going to do is just use backward induction. All right. So we're going to start with Andre, who says, okay, if I play up, we want to know, is Basie going to play top or bottom? Okay. If she plays top, then we know that Andre is going to play high because he gets a payoff of 10 and not low. If Basie plays bottom, then Andre's going to play low because he gets a payoff of 5 and not 4. So we can trim that high branch for Andre. And so now what we want to do for Basie is compare the payoffs from when she plays bottom and Andrew plays low compared to when she plays top and Andrew plays high. So we can see that 7 exceeds 5. And so we're going to go ahead and trim that top high branch for both Basie and Andre. All right. And we see that if Andre plays up, Basie will play bottom and Andrew will play low. All right, now we want to compare that to the other side. So let's say that Andre plays down and Basie plays top. In that scenario, we're going to see Andre play low because 22 exceeds 13, so we can trim that high branch. If Basie instead plays bottom, we're going to see Andre play high because 7 exceeds 2, and we're going to trim that low branch. Next, now we want to look for Basie. Is she going to choose between top or bottom? Knowing that Andre will play low when she plays top and play high when she plays bottom. All right. So her payoffs are the second listed, and we can see very clearly she's going to prefer that 25 to the 5. So we're going to trim the low and top branches and see that Basie will play bottom when Andre plays top. Now for Andre, what we're going to do is compare his payoffs between playing up, which will be followed by Basie playing bottom and himself playing low, which gets him a payoff of 5, to the scenario where he plays down and Basie plays bottom and he plays high, which gets him a payoff of 7. And we can see 7's going to be greater than 5, and so we can trim these additional branches, and we see very clearly here what the equilibrium will be. And Andre will play down, Basie will play bottom, and Andre will play high, giving Andre a payoff of 7 and Basie a payoff of 25. All right, with that, that's all of our practice questions for game theory. You're going to see some on Canvas for you to practice with as well. Please reach out if you have any questions on these practice problems. Okay, and I will see you all on Thursday.